Hello everyone, welcome to mathematics session. In this session we're going to learn about Pythagoras theorem or Baudayan theorem. It is a very important theorem for 10th class students, especially those who are going to appear for public examinations. So in examinations you may be asked like state and prove Pythagoras theorem. So in that you have to write a statement as well as its proof. So be focused, stay focused, and you can easily write it without much practice. So carefully watch all the proof. Okay, before actually going to prove this theorem, let me show you the image of the famous Indian ancient mathematician Bodhayana, who had been credited for stating this relationship. That's why we're going to study the relationship amongst the sides of a right angle triangle, the wonderful relationship he had discovered and expressed in his writings. So it was done well before Pythagoras' time. So however, later Pythagoras came out and discovered this relationship and restated and proved it in a rather logical way. That's why it is established as Pythagoras theorem. And we also sometimes we use the name of Bodhayana on his name, Bodhayana theorem. So whatever Pythagoras theorem or Bodhayana theorem, we're going to have the following statement. Right. Let us state Pythagoras theorem as follows. In a right angle triangle, the square of the length of the hypotenuse is equal to sum of the squares of the lengths of other two sides. Let me repeat. In a right angle triangle, square of the length of the hypotenuse is equal to sum of the squares of the lengths of other two sides. No confusion. Let me take a right angle triangle ABC, which is right angled at B, and obviously the side opposite to the right angle B is hypotenuse, longest side. So AC is the hypotenuse and AB and BC are the other two sides. So according to the statement, AC square is equal to AB square plus BC square. This is what we're going to establish as our proof. Right, let us start proving this theorem. So for this, what we have to do is we take a right angle triangle ABC in this manner for our convenience, right angle at B. From D, we draw a perpendicular line to AC to meet AC at D. So yes, we have drawn a perpendicular line BD to AC. So what happens, this BD, this perpendicular line or altitude you can call, has divided our original right angle triangle into further two right angle triangles. You can easily observe that angle BDC is equal to 90 degrees on the right of your screen, and angle BDA is also 90 degrees on the left of your screen. Therefore, we have two more right angle triangles. One is ADB, since it has a right angle in it, and also a right angle triangle BDC. So you can easily observe that by drawing an altitude, we have divided our original right angle triangle into two more right angle triangles. So what happens? Right, what happens? See, here we can see the newly constituted right angle triangles by drawing the perpendicular BD. See, one is nothing but from our left of our screen, and one is nothing but from our right of the screen. So here you can find three right angle triangles: original triangle ABC and triangle ADB. For convenience, I named like that, ADB and triangle BDC. Okay. Okay, since our original right angle triangle has been divided into two more right angle triangles, so the triangle on the left side has been named as ADB1, and the triangle on the right side of the screen is named as B2DC. No confusion. I'll clarify you further. So what we do is, right here, what we're going to do is we individually compare our triangles with our original triangles. So first we compare triangle ADB1 with our triangle ABC. Here you need not confuse about what is B1 and B. Actually, in terms of positions they are the same, but in terms of angles they are different. However, here you can easily find that AB is equal to AB1. Okay, let's try to compare this ADB1 and ABC, whether to find any similarities exist or not. So here you can easily see that both have a common angle A, and of course ADB is a right angle triangle and ABC is a right angle triangle. We have a right angle as their common feature. So angle B is equal to angle D, which is 90 degrees, right angle. So by angle similarity, we can easily conclude that triangle ADB1 is similar to triangle ABC. So both are similar triangles. What happens? The obvious consequences of similar triangles. Let's say, right, just now we have proved that triangle ADB1 is similar to triangle ABC. So what are the consequences of similar triangles? Yes, we know that corresponding sides are in the same ratio, or we can say that corresponding sides are in proportion. So here if we consider AD, its corresponding side must be AB. Got it? AD and AB. You can easily see that AD's corresponding side is AB. In the same way, AB1's, that means hypotenuse, corresponding side is must be the hypotenuse of the other triangle. So AC. Therefore, we take AD by AB ratio, AD to AB ratio. AD by AB is equal to AB1 by, hypotenuse AB1 by AC. Okay, anyway, AB1, I told you earlier, AB1 is equal to AB. Both lengths are same sides. So in place of AB1, I took AB. So AD by AB is equal to AB by AC. On cross multiplying, we can get AB into AB is equal to AC into AD. And further, AB square is equal to AC into AD. Likewise, we took the triangle on the left side, and compared it with our original triangle, and obtained a conclusion here that AB square is equal to AC into AD. So remember this. Right, on the same lines, we took the other triangle, which is on our right side, B to DC, and compare it again with ABC to find any similarities between them. So in triangle B to DC and triangle ABC, we can easily see that again both have a common angle C, and both have a right angle in them. So obviously by angle similarity, we can conclude that B to DC is similar to triangle ABC, as we did earlier for our first triangle. So in the same lines, therefore triangle B to DC is also similar to triangle ABC. So when we have similarity between two triangles, we can safely conclude that their corresponding sides are in proportion, or their corresponding sides are in the same ratio. That's why if we take DC in the first triangle, if we take ratio DC to the its corresponding side BC in the second triangle, that is DC by BC is equal to obviously B to C by AC. Both are nothing but hypotenuse. Therefore, anyway, we have B to C is equal to BC. You can easily verify that. Therefore, in place of B to C, we write BC. Therefore, DC by BC is equal to BC by AC. Again, we cross multiply, we get BC square is equal to AC into DC. So we have arrived at another conclusion by comparing our second triangle to our original triangle. So BC square is equal to AC into DC. Now, piling up those two conclusions, that is, first conclusion AB square is equal to AC into AD, and the second conclusion is BC square is equal to AC into DC. And if we add them, AB square plus BC square is equal to AC into AD plus AC into DC. Take AC common, so we get AD plus DC, AC into AD plus DC. Anyway, you can easily see that from our triangle, AD plus DC is nothing but AC. So replace AD plus DC by AC. So we get AB square plus BC square is equal to AC into AC, that is AC square, which is our desired result. So likewise, we have proved that in a right angle triangle, the square of the length of the hypotenuse is equal to sum of the squares of the remaining two sides. Thank you.